So inserting into a minimum heap, I have to be very specific about what type of heap that I'm using on this, and that's because of the algorithm. Now most of the algorithm, even if it was a max heap, is very similar, but it's a comparison portion of it that frankly would be completely different and completely opposite. So in the algorithm, and this is the other neat part about this, so think if you already have a data set and you're adding more data to it just live, which is great. That's one nice feature that we can have. But number two, let's pretend it's just data that you know you're probably not going to end up using. So it's still going to do a partial ordering and a binary tree. So it won't take long to insert. And also, frankly, it may not interact or interfere with a lot of the real data that you have. So it'll be a partial ordering. We'll get it in there and then we'll figure it out later. So again, that saves us a ton of time compared to making sure it's in exactly the spot that it needs to be. We can kind of cover that later or not. We may not need it at all. So that saves us a lot of time in that. So here's the algorithm. If we were to add a new number or a new data set to the overall list, I know some saying list, but it really is a heap here, but we're using a list. What we would first do is that we would put it in the next available spot. So that would be index number 12. Now, where is index number 12 in this tree? It's coming up now. So notice it's at the very bottom to keep the complete tree, which is also very, very important. Now I'm not done yet. That's just the insertion phase. After that is the percolate phase. Once we get that item into the spot, we have to double check to see that its parent is less than our newest piece of data, because that's the only partial ordering that we have. So we're going to do what is called a percolate. Is again, if the value is less in a min heap here, then we'll do a swap to move up, frankly, the rest of the tree. And I'm going to show you that here in a minute. So let's pretend we're inserting a new value called 6. Now this is a minimum heap. So that 6 eventually should probably end up close to the top, if not all the way to the top. So first, when we insert 6, you're seeing it highlighted now, we put it at the end of the array and then reflect that in the graphical representation of the tree. So 6 is right there as it's being circled right now. There's no other, by the way, that's it. That's the part of the algorithm. There's no other fudge factors. The tree will always be complete as you see each of these examples. So there really is only one spot that's really going to be put at first, and that's the placement phase. Now is the percolate phase, and when we get to the percolate phase, all we're doing is checking to see if, frankly, the parent is less than our current newest value that we put in. Well, 17 is not less than 6, so what are we going to do? Well, remember that swap function I was going to tell you about? We're just swapping two data items within a list or an array or whatever you want to do it. So we're going to go ahead and swap the two as you see right here. Very simply done. I'm not done yet. And here's recursion. Is that frankly, I got to keep checking all the way up the tree to make sure that really 6 is in the right spot. Now we check our parent again, our new parent this time. Our new parent is 5. So, well, frankly, 5 is less than 6. So we're in good shape after that. No more swaps or going up the tree is really needed because, well, frankly, we have our partial ordering that we're looking for. So that is how we would build or percolate, insert into our binary heap, min heap.